Hi, welcome to Modeling and Simulation of Dynamical Systems at the Czech Technical University in Prague. In this video, I would like to frame the whole course. That is, I would like to fix the terminology, I would like to explain the motivation, and I would like to restrict the scope of the whole course. So let's start with the terminology. In this course, we are going to talk about systems. Therefore, we need to fix the definition of a system right at the beginning. You can find many sophisticated definitions in the literature, several pages long, but I think there are a lot more useful things to do in life. Therefore, I would like to offer this intuitive engineering definition of a system. So, system is a subset of physical reality that we declare to be a system. Sounds silly, right? But surprisingly, it's actually quite functional and accurate. Its abstractness is one of the strengths of systems theory, well, and its weakness too. But in order for this definition to be really useful for us, we need to add two more attributes. They can be actually shown to follow from this abstract definition. Anyway, the first of them is the system's boundary. With the system being a subset of physical reality, we need to specify its boundary. You will see later in this course that we are going to consider systems for which the interaction between these systems and their environment is by means of energy exchange. Therefore, we need to set the boundary or describe the boundary carefully and accurately. Please note that the system boundary need not necessarily coincide with the surface of the actual physical object, such as a combustion engine or an aircraft. For instance, the response of the aircraft is actually given by the interaction between the man-made product, the aircraft, and the surrounding air. More on this later. The other attribute that we need to add here comes from the observation that however small your subset of physical reality is, you are still not interested in all aspects of its behavior, right? For instance, if you are considering a robotic manipulator for the purpose of control design, you are not really interested in how some chemical contamination of the material from which the robot is built, how it changes in time, right? Most probably what you are interested in is how the robot moves, how it accelerates, and what force or torque it develops, right? So this can be captured by specifying a set of physical variables that are of interest for you. So this is the other attribute, physical variables of interest. So for example, angular velocity, acceleration, torque, or whatsoever. Fine, so these two aspects, or these two attributes, now constitute a fairly accurate and practical definition of a system. So we can now proceed to another keyword in our course, which is dynamical. Similarly as before, I will make a reference to our engineering definition and our engineering intuition, and I will define a dynamical system as a system for which its response to changes in external or internal conditions evolves in time. So it does not happen immediately. It takes some time to evolve. You could observe some sort of sluggishness in its response, even though this is not exactly identical to delay. You know what, I will give you something more rigorous in really just a second. Let's now move on to the other technical keyword, which is modeling. So modeling for us is a process or activity which leads to a model. And a model for us in this course means exclusively a mathematical model. This mathematical model comes in the form of equations. So at the end of the day, what we are after are equations, right? And now I can give the promised a little bit more rigorous definition of a dynamical system. So dynamical system is a system which is modeled by equations when some of those equations, at least some of the equations, are differential equations. So let's now do it this way. So differential or in full generality, this need not be only differential equations, but let's say differential plus some nonlinear, possibly algebraic equations. So the last keyword which is simulation. And we are done with the terminology. So simulation, it's nothing else for us than experimentation with a model. Experimentation with the model. So similarly as you would do your experiments with the actual hardware, with your gadget in a lab, bringing some inputs, voltages, currents, temperatures, and observing the responses, some other voltages, currents, velocities, torques, whatsoever. So you can do pretty much the same with the mathematical model, although here you do not have to go to the lab. Instead you just boot into your computer. So instead of oscilloscopes and multimeters, here you use some numerical solvers for differential equations or combinations of differential and algebraic equations. Alright, so now we have the terminology set and we can move on to motivation. You know, in generally it's good to state the motivation explicitly. And this holds for our course too, because after all, modeling, you can view modeling as kind of a process where you encode your knowledge about the physical world into equations. And as such, this is a skill that is mastered by most, if not all, engineering and scientific disciplines, right? So what then sets us apart? So what is the reason for actually including this skill in our field of control systems, automation, robotics? What we have no, there is nothing like our own domain, right? And all these aerospace people or chemical engineers or mechanical engineers, they all have their own domains, physical domains, in which they are at home, whereas we are not. So still there is quite motivation for us to develop the skill of modeling, and that is control design. Our ultimate motivation for studying and for pursuing modeling is to assist in control design. It's really good to keep this in mind, because it's the only way how to avoid whatever overkills, mishits, and later frustration whatsoever. So now, how could modeling help us in control design? It can be actually useful at several stages of control design. First, at the very initial stages, it can help us develop some insight. For this, you typically build very simple, crude model which only captures the very essence of the dynamics. But even such a simple model can really help you understand the essence, the fundamental relationships in the model. It can also help you to see some inherent limitations in achievable performance. And in situations where the design of the actual system to be controlled is not finished, it also gives you an opportunity to raise some suggestions to the designers. For instance, to buy and use a different actuator and to buy more sensors and place them here or there. So let's call this design suggestions. So even though you are not the one who will design the system, it's still good to be there at the very beginning and understand the physics of the problem. Another opportunity for modeling and motivation for modeling in the whole control design process is the actual design of the controller, something that we call model-based control design. Here, the model, the equations, they constitute an input to the computational design procedure which gives you the controller, or at least its coefficients. For this, your model is, let's say, of medium complexity. It's more detailed than the initial rough model, but still it's not it simply does not have the full complexity. Very often we approximate nonlinear systems by linear ones. We very often neglect the fact that the coefficients of the system vary in time, and so on. And finally, the final opportunity for modeling is actually at the moment where the controller has already been designed and you are about to implement it. Before you do so, you would like to verify that it will work with the original system, because you did your control design based on some simplified model. So now let's call this opportunity as simulation based validation verification. For this, you need the models of highest complexity. Sometimes these are referred to as high fidelity models. So these are three major opportunities for modeling in control design that I can think of. The list is probably not complete from the perspective of where else you can use your modeling skills. The one that comes into my mind immediately is something called monitoring and fault detection. This means that your high fidelity model of your system is run or simulated in real time, and the outcomes of the model are continuously compared with the outcomes from the real plant, from the real system. And if some statistically significant discrepancy is detected, it can lead to some alarm or whatsoever. Fine, so that was the motivation. Now, obviously we cannot handle all kinds of systems, so we need to restrict ourselves somehow. So what types of systems are we going to consider in this course? Well, we are going to consider systems for which the concept of energy makes sense. As simple as that. And let me immediately explain what kind of systems we are going to omit. So we are going to skip systems for which it's the information rather than energy that is, let's say, descriptive or characterizing what's going on with the systems, how the systems interact with each other. This class of systems that we are going to omit contains systems such as various economic systems, biological, social networks, and similar. Apparently for none of these energy really makes much sense, or the information is more important. So this seems like a loss, but actually the fact that we are going to restrict ourselves a little bit, it will enable us to do more with this smaller class of systems. First, relying on energy will allow us to consider multi-domain systems. That means systems for which their subsystems come from different physical domains, such as mechanical, electronic, hydraulic, thermal, thermodynamic, whatsoever. So let me finish this first. So mechanical, electronic, hydraulic, thermodynamic, and so on. The other important consequence of considering just energy-based systems is that we will be able to model complex systems by decomposing them into subsystems, and the subsystems then into components. So again, I'll finish this. In other words, it will allow us to apply hierarchical or modular or component-based approach to modeling, if you like. Again, you will see pretty soon what this actually means. Now, so these are the systems that we are going to consider and the systems that we are not going to consider. How about the approaches? So our course will be based on 3 pillars, 3 major approaches to modeling. They will all rely in some sense or another on the concept of energy. The first and the foremost, most prominent approach in our course is something called, it's a graphical approach, and it's actually called methodology based on power bond graphs. Sometimes just bond graphs. So it's one pillar. The other one is perhaps quite familiar to you. It's quite popular and widely mastered by specialists in various engineering and scientific disciplines, and it's called perhaps analytical or sometimes even classical. And this is the approach based on the so-called Lagrange methodology. And finally, the third approach is the one based on software. In particular, so in particular on a concept of the so-called object-oriented object-oriented modeling. A prominent example of this approach is a language called Modelica. There is also another implementation of the same concept, which is called Simscape. It is implemented by the MathWorks company, the producer of MATLAB and Simulink. There might be some more implementations, but these two are the two that are of most interest to us in this course. So, graphical, equations, and software. Alright, so let's now move on to the last point in this video, and that is what kind of systems we are not going to consider. What kind of modeling approaches we are not going to consider. Well, I'm sad to say it, but in this course we are not going to study, learn, use something called system identification. If you are not familiar with this terminology, so system identification is in fact modeling methodology which is based on the data obtained in experiments. So if this is your system, you feed it with some input, which is some signal like this, and you observe and record the responses called outputs. So again, some data. And then system identification provides you with tools how to use these input and output data to get a mathematical model. Not only the coefficients, but also perhaps the structure of the model, order, whether it must be linear, nonlinear, time varying, whatsoever. Although this could be quite interesting, we have to skip this in this course, mainly for the capacity reasons. The framework of system identification requires good background in probability, statistics, random processes, and we just have no time for that, and I don't want to rely on you to have these. There's also a second motivation for skipping this modeling approach, and that is that in some sense their philosophy is somewhat orthogonal to ours. I'm not saying wrong, I'm saying orthogonal, in a sense that maybe complementary, but simply our motivation, as I have already explained in this video, one of our motivations for modeling is to get physical insight into the physics of the problem, which is something that this data-based modeling cannot give you. And that's it. So now you are ready to move on to next video, where I'm going to discuss or introduce, or perhaps even just recapitulate basic formats of mathematical models.